let's get started with Don. Thanks.
Okay, hi everyone. Welcome to the F-Sharp in Finance event here. Where's Andrew Shepherd? Is he here with us? He's on the camera, the organiser of the event here. So great, thank you to Andrew for inviting me to talk at this event. I'm going to kick off the program today with a fairly, not a deeply technical talk, but more of an overview of why I'm a passionate believer in the role of functional first programming in the finance industry. And it's based on observations that really from the last 50 years, you could say 50 years ago, in some way functional programming has been playing a role in finance for a very long time. But actually observations of over 50 successful adoptions of F-Sharp in particular in the finance industry and in related, some overlapping and related areas as well. So I want to make some simple observations about the role of functional first programming in particular parts of the computing industry, the software industry. I'm not a believer that in one tool for all purposes. Okay, I obviously am known as the initiator of the F-Sharp language design. I'm an ongoing contributor to F-Sharp and the F-Sharp community, both in open source work and at Microsoft. And although my focus is on F-Sharp and on functional first programming, I'm not a believer that we only bring one tool to solve all our problems across the entire software domain. Software is an incredibly heterogeneous kind of landscape. There's never going to be one programming language to rule all of the software industry. That's entirely clear. But I am a very strong believer that functional first programming has a very important role in certain parts of the software industry. And the purpose of this talk is to bring out ways we can think about where functional first programming is particularly effective and how that matches data from case studies, from anecdotes, from adoptions, from customers, as we've actually seen F-Sharp and other languages, such as other functional first programming languages, achieve important business results in the industry. So we're talking in the areas of quantitative finance, analytical programming, calculation engines, financial engineering more generally, trading engines, for example, with F-Sharp and associated technologies. We want to focus on the business perspective and its correspondence through the technical features of functional first programming. Based on informal observations of lots of successful F-Sharp adoptions, many of the same lessons do hold true for other functional first programming languages. There may be, I'm sure in the audience, we've got people who are experienced with successful use of other languages such as Camel, Erlang, Clojure, Scala, Haskell, and others for various kinds of problems in the software industry. And I'm not going to include many examples drawn from those communities, but I'm always glad to hear about examples of where functional first programming has made a big difference, no matter what the language. It's the techniques, ultimately, that matter. The languages, the particular implementations in various languages have their strengths and their weaknesses, but to me, the key thing is what we're bringing to the industry as we transform the industry through these tools. I want to run through using a fairly standard methodology for communicating complex products. It's one I quite like. It's a SPIN methodology, situation, problem, implication, need. It's a very nice book based on selling complex computer systems in the 80s and 90s. And I find it's, for someone who's basically a technical guy, I found this a very useful way to stand back and look at the business side of why programming technologies make a difference in practice. So part one, what's the situation, what's the problem? So the recurring business situation we're talking about for functional first programming. This is the areas of the programming landscape where we repeatedly see functional first programming making a major business difference, and that is people leading teams who are developing these kind of things. The things I mentioned before, the financial models or insurance calculation engines, or a trading platform or an algorithmic trading system. Looking a little bit more broadly, we might be talking in sort of machine learning domains, such as an online recommendation engine. We might be talking algorithmic programming, say in bioinformatics algorithms. And that ... that is at the bottom can be filled in with many other areas that are sort of overlap in spirit with a lot of the kind of work that goes on in financial software development, in quantitative finance programming, but is actually outside the finance domain. So I started off with the kind of the financial aspect, but functional first programming can be applied to other areas too. And the way I like to summarize that is really the words analytical components. Okay, and I think that's a useful catchphrase that covers not only in the components in the finance industry, but across more general areas. So the way we like to think about things in the F# world is we have this layer of fairly standard breakup of software systems. We have data information services on the left or at the bottom of the stack. We have this code analysis algorithms of maybe parallel programming in the middle, and over on the right we have this presentation, publication, and UI layer. And in the middle we have lots of analytical programmers and data scientists, and it's really here where F# as a language, certainly F# 2.0 is primarily focused. Here we might have data engineers, and over there on the right we have design. So so given that situation of analytical components, what are the problems in that domain? What do people in any particular instance of that area? Of course, you've got very concrete problems, particularly related, say, to bioinformatics, or particularly related to implementing trading engines. But the recurring business problem, the number one problem, is of course time to market, or you might also call that, if you're doing more data science, the kind of work, it might be time to insight for your data analysis. So time to market and time to insight. Efficiency is of course a key concern in those domains. You want the speed of execution of those components often dominates as a business problem. Correctness is clearly a primary concern for this kind of software, and perhaps the most recurring and the problem in those domains is about the complexity of those domains and the level of intellectual ability needed to work in those areas. So those are the problems that seem to dominate all the people who have been coming to F#. They're coming to functional first programming in order to address these problems in some way. But there's a question we need to ask first, is about whether those problems are actually serious business problems or not. I mean, we all have problems in many different problems in our working lives, and we have to be sure that we're focusing on the ones that actually map through to real-world business problems. So, is time to market a real problem for analytical components? I mean, depends a little bit on your situation. Some people have the luxury of spending 3 or 5 years to try and solve a particular problem in a business domain. They're unconstrained by time, but I think all of us in practice, in nearly all working lives, we're deeply constrained by the business situation and getting a solution to an analytical problem to market. If we have late models, okay, then we may simply not be able to enter a trading opportunity. We may not be able to enter a market. If we're not providing services on time, implementing those services in a company such as Thomson Reuters or Bloomberg or other information providers, that we're going to be missing opportunities to participate in information markets. And if our actual products are simply not delivering on time, then the whole software business can be a failure because competitors get to market first. Is correctness a problem? In some parts of this domain, surprisingly, correctness is not seen to be the number one problem. Even in algorithmic trading, for some people, they're willing to say, actually, we don't mind if we're not valuing correctly or on time, as long as the algorithms make their money. And then, of course, some actual catastrophe happens where the system either runs away in some way, or some deep bug of dividing by 2 instead of multiplying by 2 or something, as happened in a multi-billion-dollar loss recently, can cause a catastrophic problem. So correctness, but more generally, correctness is perhaps is one of the 4 crucial problems in this domain. If you have buggy models, it maps through to incorrect values, risks, and trades, and that can put entire businesses at risk. It can cause partial loss from day to day. It can cause catastrophic loss. Buggy services can cause reputation loss, and buggy products can cause loss of customers. There's efficiency of problems. Slow models might mean you're simply not able to value the risk position, the risk and valuation position of a financial institution in the overnight runs that are necessary. You may not be able to provide real-time information to the business decision makers. Slow services mean you can't scale out, and slow products lead to all sorts of problems and all sorts of software, of course. But perhaps the one we don't talk about enough is what about complexity? What are the business ramifications of not being able to tackle complexity in your software projects or in your analytical components? And if you simply can't model a particular set of financial instruments, you can't implement your services, you can't implement your products. I mean, broadly speaking, we'll just talk about that as failed projects. It can also lead to, I think, this lack of belief from a business perspective about can your people even tackle this kind of problem? Okay, and if you want to have the very best software teams that can approach problems with confidence, knowing that they've got the tooling which allows them to tackle complex software problems. And you will be hearing a lot about that, I think, from John and from others, about how in practice tools in the functional first programming domain help people to tackle complexity and therefore give teams more confidence in the kind of problems that they can solve. So the recurring problems: time to market, efficiency, correctness, and complexity. Now, something we don't, on the complexity issue, it's where we stop back and think about this thing about many tools or one tool in the software industry. There are whole swathes of the software industry where complexity is intrinsically a bad thing. Okay? User interface design is a classic one. Okay? We don't want more complex user interfaces. We want more simple user interfaces. Okay? And although functional first programming is a perfectly fine tool to implement some user interface work, the overriding imperative there is not to build more complex systems, but to build more simple systems, or not to solve more complex problems, but to solve design and user interface and usability problems. Okay, so so when we map back and look at those areas of where functional first programming is being successful, it really is in areas where solving complexity is the overriding business concern. Okay? And that's not the case in user interface programming, and therefore we don't particularly see strong uptake of functional first programming in user interface programming. But we do see strong uptake of functional first programming in areas where solving complexity really matters, in addition to these other business problems. So the need is for analytical programmers delivering correct, efficient components in the enterprise on time. And that's the set of problems that functional first programming helps solve. It's always been the bread and butter of functional programming historically. And in the last 10 years, we've seen this rise of this class of implementations of functional first programming in F# and Scala and in Clojure and other systems, which allow real-world adoption of these techniques in appropriate niche and or but we're not looking to solve all problems in the software industry, but in particular areas of analytical programming. So why is functional first programming a fit for these set of business problems and these needs? So observation number one is simply that the core of every single functional first language is about simple, correct, robust code for solving complex problems. When you go through the design features of any functional first language, you'll see that this is at the core of the problem. If you take, for instance, some code which is taking an event stream of data coming in, doing mapping and transformations over that data, and then sending that through to some to the next stage, to the next system in the service pipeline. The language features which have been used to express solutions to the code are about giving simple, declarative, robust solutions to what might otherwise be seen as a complex problem. Complex problems just boil away, especially they boil away so the essence of the problem, of the solution to the problem, is seen in a coding form. So in this case, what do we mean by functional first? We mean programming models and tools that embrace functional programming as a primary tool for solving problems. And I've mentioned some of the examples here. Haskell should also be on the list here of examples of those programming tools applied to these domains. So observation number two is that it is about a particular kind of implementation of functional first programming, about these languages which are highly interoperable. So highly interoperable implementation of functional first programming allows rapid, non-intrusive deployment and integration of components. And this is perhaps the most the key aspect of the design of F# as a language. It also applies to some extent to Scala and Clojure as languages. But F# in particular, you can, F# is fully interoperable with its host language. C# interoperates with a very surprising number of other systems, as we'll see in other talks today and later on in this talk as well. But you can also take your F# code and you can wrap it up as a .NET component and deploy it into a .NET system or into a service-based architecture very, very simply indeed. And that means you can encapsulate the use of functional first programming techniques into areas that are appropriate without infecting your entire organization with having to know these techniques. You can encapsulate and use the techniques where they are most effective. So interoperability, crucially, removes entire phases from the analytical software development process. We consistently see people adopting F# who had previously had a methodological pipeline where they would do their modeling in R or Mathematica, perhaps Excel, and they would be translating Mathematica to C++. So they'd have a 6-month turnaround cycle from the actuarial experts through their deployed systems, because they have to do translation, because they've got 2 phases in their software development process. And that can now be replaced by a single phase process where F# is used for the analytical software, both effectively the experimentation side of the work. Of course, you can still use R and Mathematica and these other tools as part of your experimentation if necessary. You can be transitionary if necessary. But the ideal is to remove these 6-month transitions out of your software development process by adopting tooling which is interoperable. And there's very few other ways you can get rid of months out of your delivery process. And some of the biggest gains we've seen is through this interoperability process. A key aspect of the design of these strongly typed versions of these functional first programming languages is that they maintain efficiency by design. A language like F# has a performance as good as C# and Java, and sometimes as good as C++. And that is by design through the propagation of strong typing throughout the software, throughout the language design, and through into the runtime system that's used by F# and shared with C# the .NET runtime system. So observation number 4 is strong type languages help analytical programmers tackle more complex problems. There's a whole range of language features that are built to make this true, but just to pick on 2, you spend a lot more time in the domain and a lot less time thinking about null pointers and object hierarchies in particular. So by removing this sort of sea of incidental complexity that arises, in particular in the object-oriented programming languages, focusing on functional first decomposition as the primary technique, removing nulls and object modeling as a, yeah, they're still there. You can still use object modeling, and if you look around, you can still, in the corners cases, actually use nulls as well, where you have to for occasional performance reasons. But it's extremely rare to do that. And instead, you land people in the sweet, productive spot right at the start of their work. So how functional first helps is simple, correct, robust code. Interoperability eliminates entire phases. Strong typing gives efficiency. And analytical developers are empowered to solve complex problems, or to focus on complex problems rather than incidental complexity. So I want to take a look at some examples of how this works in case studies in practice. I'll run through these quickly to just leave a little bit of time for a quick demo at the end. And the first example is from a power company here in the UK, an application to balance the national power generation schedule. It's a calculation engine written in F#. I presume it's deployed either as a web service or in the context of a C#, some kind of C# Visual Basic application. And the use of F# to address the complexity at the heart of this application demonstrates the sweet spot for the language. Algorithmic analysis of large data sets. Now, Simon Cousins here took the time to draw out a whole bunch of how this maps through technical features from interoperation, units of measure, unit testing, parallelism, and so on. What I like to do when people write up summaries like this is to condense it down to these 4 top-level points. Time to market. So the interoperation is really about time to market, time to delivery of the component. When he talks about units of measure eradicating a whole lot of bugs, let's just step up a little bit and think that's about correctness. And again, you see these themes coming out. Exploratory programming, time to market, time to insight. Correct unit testing, again, getting correctness. Parallelism, getting the efficiency you need as a business result. Code reduction, time to market, lack of bugs is correctness. And you can do this with case study after case study. There's some great case studies in F# in finance. I particularly encourage you to look at the fsharp.org testimonials, and there's a lot of testimonials about the role of functional first programming in financial programming. And we'll be hearing a lot more about that today from in the different talks we have on today. So, but again, the same themes come through: time to market, efficiency, and correctness. F# in insurance, this is someone who works for a large actuarial company. Despite adopting all the latest agile Scrum techniques, the projects have the usual delays, complications, and sometimes failures. We used F# and created a system which performed the necessary calculations highly efficiently in parallel and with a perfect match to the spreadsheet results. And again, mapping through to language features, immutability, easy parallelization, expressiveness, testability, conciseness, flexibility, productivity. It's up on fsharp.org testimonials. And you can, again, you can see that's again about time to market, tackling complexity, avoiding project failures, by choosing tools that help you tackle complexity and focus on the real business problems, and efficiency and correctness. Sharp in a finance trading platform, again, solving problems in days that would take weeks using more traditional languages, and solving complex problems in an elegant and highly maintainable manner. Just to say that this is not all about F#. As I said, this is talk about functional first programming. You could actually bring in many case studies, I'm sure, from Clojure and Scala as well. One case study I like to talk about is an older one from OCaml at a company called Jane Street. The quantum group has been using OCaml since 2002 with good results. And they rolled out OCaml more generally, and again bringing out these themes of robustness, performance, and another theme which is about readability and maintainability. And so when they look at the evaluation, it's about efficiency, and again this thing about new systems, implemented strategies more complex than previously possible. And what I like about that comment is, of course, we can assume that that actually was mapped through to a real business result for this company as well, that actually implementing more complex things made them more money, okay? And that's, as again, that doesn't apply to everywhere in the software industry. It doesn't apply to user interfaces, but it does apply in financial work, and especially in actuarial and in insurance and in investment banking, quantitative finance, financial engineering kind of work. Looking a little bit outside the finance domain, F# in biotech, this one's interesting because it makes a comparison with Python. Python's a great system, but F# brings a lot of technical advantages over a system like Python. In particular, because it's strongly typed all the way through, then straight up F# code tends to be more robust and to run faster in a like-for-like comparison. So efficiency, correctness, and time to market, and efficiency of performance, some F# uses of Microsoft, F# advertising, ranking, and rating techniques, which can also be applied in financial markets. They're talking about rapid development of prototypes to verify the underlying mathematical models. This is some game theory implementation in auction simulator. It's the auction simulator used for the ads that we display on Bing and other web-based assets where Microsoft get the opportunity to display ads. And again, they're talking about the role of taming complexity. They're saying complex algorithms such as ... Nash equilibria can be expressed succinctly, and various language features are used to reduce the chances of errors. F# at Kaggle, an iconic data science company. Again, look at f#.org testimonials. You'll see that they're talking about taming complexity, fewer bugs, and time to market and productivity. And the last one is F# for machine learning at Microsoft. Again, part of our ad auction pipeline. The click prediction system used in Microsoft Ad Center. Again, the system was written by one of Microsoft's distinguished engineers, Dr. Patrice Syme, who's a big advocate of F# and its role for this kind of analytical programming work. Speed of experimentation. He brings out it's easier to debug in a distributed and parallel environment, and he calls F# liberating and exhilarating for this kind of work. So the data agrees: simple, correct, robust code, interoperability improves time to market, strong typing gives efficiency, and analytical developers are empowered to solve more complex problems. Okay, so in the last 10 minutes, I think I've got 10 minutes of the talk, I'm going to just step back to look at F# in practice a little bit. So today you're going to hear about functional first programming, particularly with the focus on F# for all sorts of things: trading engines, GPUs, scaling, cloud programming, DSLs for insurance and risk, functional first programming plus QuantLib plus Excel, and functional first programming for data science. I'm not going to talk about those particular domain areas, but I do want to talk a little bit about something I've been doing as sort of the foundation layer, which can be used in nearly all of these areas, which is about this functional F# deep data integration. It's a language feature called F# type providers. It's kind of my role in being the, I guess, contributing at the language level of the design to be able to tackle very fundamental problems that run across many different areas of software development. So we all know we live in an information revolution. This is one way of, in the open web services point of view. If we look at the numbers at the bottom of the number of APIs available on the open web, we had the original when eBay first put up their sort of web-based API back in 2000, and all the way through 2011, it came from a program called web.com. There's this explosion in the web as a platform. Just one example of the information revolution. Of course, inside the finance industry, this has been going on for a long time, but it continues today. Financial markets data is like water, they say. Everyone needs it. Everyone knows where to get it. Nobody is kind of really sure how it goes. You might get washed away by it. This is true not just in financial markets, but in all information programming these days. The amount of the ocean of information available both on the open web and in the enterprise makes many opportunities, but also many, in a sense, many risks, both in the quality of the data you're getting, but also just in not being able to even tackle the problem of navigating that ocean of information. Just kind of how data flows through a typical finance operation today. We have both market data, reference data, and derived data into these data distribution platforms. So there's many things that are needed to tackle the problem of financial data: finding it, manipulating it, integrating it, analyzing, sharing, and controlling. Now, what I want you to think about is we have this terrible problem of this ocean of data, but our programming tools are fundamentally not suited to working in the information-rich world. Our programming tools are fundamentally data sparse. Okay? What that means is getting financial data into a programming language is immensely tiresome, error-prone, and in many ways it's boring and hard to get your best people to apply themselves to the world of financial data programming. So we need to bring data more generally into the programming languages. It doesn't just apply to financial data, it applies very broadly that we need our languages to become information-rich. And that has application in the finance domain as well. And we need that to happen at full web scale, at full internet scale, and at full market scale, strongly tooled and strongly typed. So what I'd like to do in the last few minutes, if everything works well on this virtual machine, is to show you some examples of that. I want to first show you an example of using F# with a non-financial data source. First, this is F# in Visual Studio 2013. I'm using some visualization scripting to allow me, for instance, to create a table of squares and display the data over on the right. And you'll also see me using some charting libraries called the F#.charting libraries, which give you as an entry-level 2D charting which fit nicely with F# data. Okay, so it's creating a point cloud of data and displaying it. So in this first example, I want to show how we turn F# into an immensely information-rich environment through this feature called F# type providers. And this reference here is an F# type provider. Okay? And this type provider allows us to access an information source called Freebase. Freebase is a web-based system that has an ontology of millions and millions of entities which may be of interest to you. For instance, if you're interested in science and technology, and you're interested in, say, biology, and you're interested in wanting to know a lot about genomes, for example, and to get your hands on data for various genomes, you can come down here and go to genes and find or many thousands of instances of that kind of data. You might be interested in books, for example. Under the books category, you'll get 3 million books, which you can query and use. You see that through the use of F# type providers, we're mapping in an external information source, which is through a web API, and we're making available in the programming environment this immense amount of data in a strongly tooled and strongly typed way. We'll see other applications of this technique later on today. But now I want to switch across to the financial domain and show how this can apply in the financial world. And I want to use a system called Xenomorph and to show you a quick demonstration of an experimental type provider for Xenomorph data. So we're using Xenomorph Timescape, which is in many ways comparable to, say, KDB or KX as a system, a vector database. We point our Xenomorph provider at a particular database. This is a database in the Azure. I'm using virtual machine in the Azure cloud system here. And once we point our programming language at the database, we have the full ocean of financial instruments embedded into our programming context. Okay. So all the data, all the time series data for all the information, for all the instrument categories that are present in the database is now available to the programming environment. So if you're interested, for instance, in equities here, you can go to GB equities, and we get this deep, pervasive ability to get strong typing and strong addressing and strong embedding right down to the individual entity level for each of the individual instruments we're interested in. So if you're interested, for instance, in tobacco, interested in, say, Sainsbury's, for example, you can get all the data that is available to the enterprise about that particular equity. We might be interested in knowing the closing prices of that equity, or its high or lows, or and the other information that's available. Once we select, say, the closing prices, we might be interested in getting something like a moving average of the closing prices for the equity. So deep, pervasive embedding of financial data into the programming language. So once we have that, we can evaluate those. Now we can do some charting with those here. Let's get the equities. Let's take a look at the values for the closing prices of Anglo-American. Those here. That's adding the dates into the bottom, so we can see the date ranges here, 2011 to 2013. Okay. We might be interested in making that a moving average by accessing the moving average property here. Now we might be interested in multiple smoothings of that data, so we start to be programmatic. We took the original data, now we applied once a 10-day smoothing and a 30-day smoothing to the data. We might be interested in comparative studies, for instance, of the volatility of two comparable stocks. This is the volatility of Sainsbury's versus that of Tesco's. Comparative volatility of 30-day range and 1-day session of 5-day trading periods. So the programming language becomes deeply, pervasively rich environment for working with time series data, directly working against the information base of your enterprise at arbitrary scale. And it even has nice features that if various features aren't, such as the risk report may not be available for AstraZeneca, you'll get a nice compile time error here telling you that that particular property is not available for that particular equity, but it might be available it is available for this one. So you're only seeing the properties that are actually available for the different enterprises, for the different assets that you're working with. Okay, so an F# type provider gives deep, simple, robust integration of financial data and many other kinds of data at massive worldwide scale, full market scale, and you can use it in cloud and on-premise scenarios. So in summary, to wind up, F# is it's an open source language, it's a fully open language, you can use it across multiple platforms, it's strongly typed, it's efficient, and it's rock solid stable. It's got unbeatable financial data integration. No other programming language in the world has the data integration capabilities of F#. None whatsoever can do the kind of data integration that I just demonstrated with Xenomorph data and with Freebase data, and we'll see that applied in other settings to interoperating with systems such as R. We'll see it applied to interoperating with systems like Hadoop and Hive. And this makes it a safe choice for enterprise functional first programming. And the Visual F# tooling from Microsoft is obviously Windows focused, Azure focused. Of course, the Microsoft team focus in their Visual F# tooling focus on those platforms. That is functional first tooling you can trust, provided by the most trustworthy vendor of software tools, which I'm very happy to work for, which is Microsoft. So questions on any of the topics I've covered, from functional first through to data integration. your question, please.
There's a survival bias in the testimonials you had there of projects at work.
Yeah.
Have you learnt anything from projects which haven't worked and incorporate that into future generations of F#? I mean, my main...
Oh, so it's hard to map through to the second part of that question. On the first part, I mean, software projects can fail for all sorts of reasons, right? One is a lack of training, one is misapplication, one is a big one is attempting to rewrite existing systems. Sometimes people get this like religion, and, you know, F# is, or you know, we're going to do everything in this from now on. That old system, which has been our pain in the neck for all these years, we're going to rewrite that greenfield. Those sort of projects can really often fail, right? Because they, to rewrite a 3 million line system, and it's just not going to get there in time with the bug-for-bug compatibility or whatever you're aiming for. So that's a big one. Another one is attempting to eliminate C++ from all aspects of your system. If you've got existing high-quality C++ components that are market tested, that have been through the regulatory process, don't replace them, just use them. The F# is an incredibly interoperable language. You can use C++ components, often wrapped via a column interop layer or something like that. But do not rewrite existing high-performance C++ code just for the sake of it if it's working deployed. So those are the two big methodological application ones. In terms of mapping through to the language features, I mean, I think with F# 2.0, we landed with a fabulous set of language features that were very effective in practice. It's the, I guess you can see that in F# 3.0, I observed this recurring need for data integration at a deeper level in the programming language. Across both, it's partly from working in the finance industry, but partly from working in just normal database programmability projects as well. And the web as a data context, or interoperating with Excel, and that sort of thing. So that was something we could tackle with the language layer. But I think most project failures, if I see people failing with F#, it's usually because of something of those first two categories, or a lack of training can be another one. I mean, if you're going to take a step to be adopting functional first programming, the key thing to do in your organisation is get training. It's an absolutely key step. In London, you are blessed to have some of the best functional first programmers in the world offering training courses through groups like Skills Matter and others, and really just get your team trained and get. It's very important to get your architects on board. Obviously, it's important to train the whole team so that everyone has a competence, rather than just having one or two people pushing this onto their team, because that probably won't be effective. Another thing that I think we need to be doing more of is getting these offshore vendors from India or from Eastern Europe, who are often used in the financial industry today. They know about F#, and they often know it, right? And there's somehow this assumption that we have, the vendor where we use from Poland can't learn F# or something. That's just so not true. Like they probably already know it, and they would be immensely productive in applying it and using it. So I think we have to be more proactive in working with the global vendors to be adopting these kind of techniques. One more question? Time for one more question? Yeah?
Has anyone used the data providers that you just showed us in production?
The financial data provider I showed you then is, it's very recent. It's actually only just been implemented this week. The data providers are used for database programming in production all the time. The talk I gave didn't quite get across the breadth of application of those techniques. I'll answer directly. So the number one use of the data provider is to do database programming. You can do SQL query, link-style SQL query programming in a very similar way. It's point the provider at a database and then it's work with the database in a fully strongly type way. It's incredibly fluid and easy to use. It's also used for accessing CSV, basic data formats like CSV and JSON data and XML data, and getting strongly typed views over those. And that is used in production by in a lot of different settings. Blue Mountain Capital, the hedge fund. Is there anyone here from Blue Mountain Capital? Okay, I know they have a London office in it's mostly in New York where they use F#. They use the type provider mechanism to interoperate through to R as a system as well, and I think Thomas Petracek's talk later today will be demonstrating that. So again, they use that in production environments. They also use it both in data investigation and data science kind of analyst environments, and they also in production environments as well.
Yeah, John, can I just make a quick comment on what you just mentioned? So, I'm Rob Fraser, I'm the CTO for Cloud Services in the UK. Hello, Stu, how are you? Very well. A quick comment on what Don just showed you. So, what we're doing, we've got an initiative going now with some of the big data providers to start surfacing as embedded data with inside Azure financial services market data. So we just saw with Xenomorph, which is our first data middleware element of that, which is on Azure. We have various data providers now working with us to provide their data into that middleware. The idea is we're going to build an ecosystem of data middleware and data providers on Azure so you can take storage, compute, and financial services data directly on the platform. It will also link directly into the Power BI program, so we actually use the new version of Excel and the Power BI and Power Max and Power Query interface, again, to access the information directly, all of which will be licensed directly with the data vendors under existing terms and conditions you have with them. So we're not got that platform public yet, we're getting close to a formal go-to-market around it, but if anybody's actually interested in that, whether it needs development or test or embedded within Excel, please feel free to reach out to me and we can talk a little bit about timelines for availability for financial data and Azure. So I mentioned that's the one.
That's great, thanks. Yeah, the work in particular with Xenomorph, to be clear, the Xenomorph provider that I showed was actually only 1 day's work. It's around 500 lines of code. It's up on GitHub under FS Projects, github.com/FS Projects. You can get the code there. It's very, very simple code to do the mapping and projection of the Xenomorph metadata through to the F# system. Now that work is, you can use it today as it's experimental, but you can take it and use it today. But one of the reasons why we're looking at tying F# into this ecosystem of data is because, which you can use today, nothing to do with Azure, but you can, as time progresses, we see Azure and the cloud platform as a financial data integration platform as well, through providers like Xenomorph, and clearly F# with its ability to integrate those strong typing information from those elements of a cloud platform makes it's a great integration tool to build our cloud services based on the back-end data systems. Okay, I think we're done.